In this lecture, we are going to start talking about matrices, which is the idea of taking things that we've already learned, like system of linear equations, and figuring out a way to make them easier to work with, right? Because in the first lecture, we talked about system of linear equations with two equations, two unknowns, and we could use elimination method or substitution method, and that worked really well. But then when we get to three matrices and sorry, three equations and three variables, it becomes a little bit more time consuming, not unreasonable. But then when you go to four equations, four unknowns, now it becomes way too much. And so there has to be a more efficient way of doing that. And that's where matrices come into play. It allows us to basically say, you know what? I'm looking at these systems and I notice that a lot of the things don't change except the numbers. So what if I just got rid of everything and only looked at the numbers? Could I still solve what I'm looking for? And the answer will be yes, we can. So matrices are all about convenience. They allow us to do things that we already could have done with other techniques, but just speed it up by a lot. And computers love matrices because it's just numbers, right? So what is a matrix? A matrix at its core level is an array of values. That's what a matrix is. Now, how do we construct a matrix? Well, a matrix is just made up of rows and columns, right? So we can say that there are m rows and n columns composed of entries in each spot. Now, what does that look like? Well, an example of that would be something like this. 1, 2, 3, 4, 5, 6. So we have a matrix and we look at it and we recognize that there are two rows. So 2. And if we look at how many columns there are 3 of them, right? And that's a matrix. Now, could you put anything inside of a matrix? Absolutely. You can put variables, names. There's no limit to what can go inside of a matrix. But for the sake of this class, we're only going to focus on numerical values, maybe a variable, but that's kind of what we're going in. And so how do we say this to anyone? We would say something like this is a 2 by 3 matrix, where the 2 represents how many rows and the 3 represents how many columns. So that's kind of the notation that we use, row by column. And so we call that the dimension of a matrix or size. So this right here is the dimension. I prefer the word size because in linear algebra, dimension has a very specific definition. And so I try to avoid confusion there, but either of them make perfect sense. And so now that we have like kind of the structure of a matrix, what we're really interested in knowing is these numbers inside, right? So we call them entries or elements. So the entry or element of a matrix is the value located in a specific row or column denoted as, and depending on the textbook, they use different letters. So something like AIJ, which means entry at row I and column J. So that's how we're going to say like what entry is in row 2, column 3, right? So this is how we're going to describe that idea. So if we do an example, just kind of illustrating what we just talked about. So given A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. What is the dimension and what value is located at A to 3? Then we can say that, well, if we count how many rows and columns, so the row by columns. I like to put little parentheses around them, but that's just an optional thing. I count and there's 3 rows by 3 columns. And then the value located at A23. So if I count row 2, where the 4 starts, so here, and then go to the third one, 6, then we're at 6. So 6. Row 2, column 3. That's going to be this number right there. And so some quick word about notation. Okay. Matrices are often denoted using capital letters and bolded. But because I can't bold here, I am going to use an underline. Okay, I use underline. So if I underline a capital letter, that to you tells you that it's a matrix. That's not, the one thing that's kind of annoying about matrices is there's no like uniform notation that we all use. Some people like to use italicized, some people like to not do anything to it, some people like to put a bar underneath it, and some people like to bold it. So there's no consistency in that respect, but the one thing we all agree on is capital letters tend to be our favorite. So, and from that, that's kind of the basic structure of a matrix. How many rows, how many columns it has, and then what is the dimension, as well as what entry is located at what location. So row by column. And so from that, we can start introducing some algebra, right? So matrix addition. So what's interesting is fundamentally in mathematics, there's really only 2 operators. There's addition and multiplication, right? Subtraction is really just the convenience of adding negatives, and division is just the convenience of multiplying fractions. And we're going to learn that in matrices, there is no division. We actually don't have a way of dividing matrices because it doesn't really work for that structure. But we do have addition and multiplication. And again, if addition exists, then you usually have subtraction because they're the same thing, just with negatives. And so with addition of matrices, we kind of have to follow a rule. So in order to add 2 matrices, A and B, kind of like fractions, they must be the same dimension. So you can only add a 2 by 2 matrix to another 2 by 2 matrix. Just like with fractions, you can only add fractions with the same common denominator. You can't mix them up because our method of adding them together or subtracting lends itself to that they have to be the exact same structure. So if you took any matrix, and again, we're going to do a 2 by 2, but this works for anything. Again, and subtraction works too. And I want you to think about it. If you got to create this rule, like you're the one inventing matrix addition or subtraction, how would you do it? Like, what would be the easiest way that you could think to add 2 matrices? And most students intuitively think, well, I would just add the top left corner to the top left corner. And the best part is that's exactly how it works. There is no trick to it. The way that you add it together or subtract is exactly what you would think it would be. Top left to top left, top right to top right, bottom left to bottom left, bottom right to bottom right, right? And so that's good. There's no confusion there. There's no fancy technique. Now, that won't be true for multiplication, unfortunately, but at least for addition, it tends to work out the way that we would want it to, right? And so the first question you always have to ask yourself before you add any matrices is, are you allowed to add them together? So here's an example of that. Given A is 2 by 3 and B is 3 by 4, what is A plus B? Right? Well, if you look, you notice that 2 by 3 is not the same as 3 by 4. So you would say it's undefined. You cannot add these two matrices because they don't match up. They don't have the same number of elements in every single spot. So we can't do anything, right? That's nice. There's no weirdness going on there. You either can add them together or you can't. So now let's do an example of adding them together with numerical values. So if I did want to add two matrices together, so something like this. And so there we go. So first, just check the sizes or the dimensions. So I just do 3 by 2, 3 rows, 2 columns. 3 by 2, I look at them, they're the exact same thing, and I can look at the matrix and recognize that. And I say, okay, I can add them together. So then you just add the top left to the top left, top right to the top right. And if you're doing these by hand, which I do recommend you at least do it a couple times, make sure that you're copying the correct numbers down. One of the biggest mistakes people make when doing these by hands is you just copy the wrong number down because believe it or not, your brain doesn't really like doing these types of calculations. It's just too many numbers. There's too much information. And so your brain will start to play tricks on you because it's just trying to get you away from it. It doesn't want to do this. So it'll start to do shortcuts because it wants to, again, get away from it. And those shortcuts can often lead to mistakes. So got to be super vigilant when doing these by hand. So we get 2, 2, 6, 8, 2, and 12. And that's how we add two matrices. Now, you can also do this on your calculator. So that's what I'm going to do next. I am going to bring up the calculator. And so you can do all of this on your calculator. So you don't actually even have to do this by hand. So if you click on second math, sorry, wrong one, second inverse, this is your matrix menu. And so the first column just is basically you picking your matrix when you actually want to use them. If you hit the right arrow key, these are all of your operations. And then if you hit the right arrow key one more time, this is where you actually edit them. So you put in the numbers. So we're going to press enter. Also, once you put in a matrix, there's really no way of getting rid of, like you can never make this look like this again once you use it, unless you completely clear out the RAM in your calculator so that it resets it. So once you use it, it's kind of going to always be there. So we have 3, enter, 2. So 3 by 2. And then we're going to move this over here so we can see. And then we just type in the number. So 2, enter, 3, enter, 4, enter, 5, 6, and 7. So we have entered in all our values. And so then we want to do second quit, second matrix, and then we're going to edit our second one. So B. And again, 3, enter, 2. Now here's the interesting thing. So the interesting about this calculator, so you press 0, you can hit the right arrow key to not move over. So if you hit the right arrow key, it's not going to move over to the right. So you always have to press enter if you want to move to the right. -1. Don't use the subtraction symbol because if you use the subtraction symbol, you'll get a syntax error. So if you ever get a syntax error, it's most likely because you use the subtraction symbol instead of the minus symbol. If you hit the down arrow key, it will move down. So left and right don't work to move when you're typing in numbers, but up and down do work. So if you prefer go column wise, you can do that. But if you want to go row wise, like across, you have to press enter. So like that's 2, down arrow key, -4. Now I got to press enter. And then 5, and then up 3, right? So pick one way of doing it and then never change because consistency is always kind of the key with these so you don't make little silly errors. So now we have done that. So we're going to quit, second quit, and then second matrix, and then we press enter on the names because that's what we want to use it. Plus sign, second matrix, this one right here. And then we get that, and that's going to be 2, 2, 6, 8, 2, 12. So that's how you use your calculator. And there's really no rule against using or not using your calculator in this class usually. The only thing is if you have variables in your calculator, sorry, in your matrix, the calculator by design isn't going to do that. unless you have a calculator that has a CAS, but technically those usually aren't allowed on the exam, so you don't want to use those during an exam environment. So that's matrix addition. Now, what about multiplication, right? And to be clear, subtraction is the same thing. You would just actually subtract the values. So that's the only difference between addition and subtraction. In fact, let's just do one real quick so we don't forget. So if you want to subtract two matrices, again, you check the size. And so it'd be 1 minus 5, 2 minus 6, 3 minus 7, and then 4 minus 8. And we get -4, -4, -4, -4. Okay. And that's how you subtract matrices. So in matrices, we're going to have two types of multiplication. We're going to have what's called scalar multiplication. And then we're going to have matrix multiplication. So the reason we have two different types of multiplication comes down to algebraic structures. And that's not really that important in this class because you're not really going to dive deep into like vector fields and all that stuff. But the whole basic principle of this is basically a mathematician said, I want to create a number system that has very peculiar properties that as long as I have these properties, I don't expect anything weird to happen, right? We have the real numbers, all the numbers that we know growing up, pi, e, 1, 2, 3, the negatives, the fractions, the decimals, the radicals, they all have very special properties that essentially make that number system complete, and we don't really run into any issues with them. And so we want that same thing with matrices. So mathematicians said, okay, we want to define this rigorous structure. And in order to do that, we need to have two operations, one for addition so that we can combine elements together, and then one with multiplication, where we can kind of manipulate elements to make them different sizes, right? And so unfortunately, matrix multiplication is very weird. And it's not consistent in the sense of like, it doesn't always work because you have to have a certain rule set to do it. But scalar multiplication always works because of how we define it. And so that's kind of why we have two multiplications. This multiplication is more for defining a structure. And then the other matrix multiplication is just a way of combining matrices through multiplication purely of two matrices, right? And that's kind of confusing. And I just say, if that doesn't make sense, that's okay, right? It's a little bit complicated and you don't really need to know it to be successful in this class. Just the basic principle of, well, what does it mean? Or what does it do, right? So scalar multiplication is multiplying a number with a matrix. So not a matrix with a matrix, but a number with the matrix, right? So what does that entail? How do we do that? Well, let's just pretend we have a matrix. So let alpha, I know that's a funky alpha, but let alpha be a number or scalar. That's another word for number, scalar. Then if I multiply a matrix like this, right? Some number times A, B, C, D, then I want you to think, okay, if I got to choose the rules, right? Like I got to choose how this would work, how would you do that? Well, me personally, I would feel like, well, this should be everything into the matrix. So that would look like this: alpha A, alpha B, alpha C, and then alpha D. And the best part is that's how it works. It works the way that we would want it to work, where we just distribute the scalar into the entire matrix. That's good. It has that intuitive notion of how I expect it to work is how it works. Again, when we get to matrix multiplication with two matrices, that goes out the window, but we get to keep it for now. So then the question becomes, okay, does it matter what side I multiply it on? Because I put it on the front, but what if I have the number on the other side, the back of the matrix? Does that make a difference? Well, it turns out it doesn't. Because if you think about it, and again, if this doesn't really make sense, that's okay. Just remember, it doesn't matter which side you multiply it on. Alpha and A, B, C, D, they're just numbers. And if you think, well, 5 times 2, well, that's 10. And then I was told as a kid, it doesn't matter which way you do it. 2 times 5 is equal to 10. You get the same thing. Like, okay, so then I can say, well, alpha times A, B times alpha, C times alpha, and then D times alpha. Like that works. Like I can reverse the order because 2 times 5 and 5 times 2 is 10. They both give me the same number. And then you think to yourself, well, if I'm allowed to multiply a number into a matrix, I should be able to bring it back out, right? That's kind of like factoring distribution, right? I was allowed to deal with reals. And the answer and the question, and sorry, and the reality is you can do that. So if you can multiply a value into a matrix, you should be able to multiply it back out. And there you go. And that's kind of the proof for it, actually. We just proved that scalar multiplication doesn't care about which side you do it on. Now, most of the time, you're going to put the number in front because it just looks nicer. Like that's just how we usually do it. But in practice, it doesn't matter what side it's on. You'll be fine. And so if that's all is confusing, again, not the end of the world. It's not going to make a difference in your ability to actually do it. So here's an example. 7 times this matrix. Well, I'm just going to distribute the 7 into every single one of them. And now we just get to practice our 7 multiplications. 7, 21, 28, 35, 49, and hopefully this is 56. It is. Okay. There you go. That's all you're doing. Now, if you're wondering, why would I ever do this to a matrix? Well, we learned in vector fields that doing this allows you to make the matrix, which we'll eventually call vectors, longer or shorter, or we can flip them around. So that's what those numbers do. They allow us to scale a matrix. So that's very useful for us. Now, if you're wondering, how do I do that on my calculator? You just take your matrix, so like 7 times, and then you just pick a matrix. So we'll pick our first one, A. And if you don't remember what A was, I'll show you. Second matrix, edit. So that was 2, 3, 4, 5, 6, 7, which I think is almost like the one that we have, just not exactly. So we have 14 here instead of 7. But yeah, that's really what it is. You just multiply it. Now, here's a cool thing about the calculator. If you don't put the multiplication symbol in front of the A like you do 7A, it'll still do it. You don't actually need the multiplication symbol there. So kind of nice. So that's scalar multiplication. It allows us to scale matrices, hence the name. Now, what if I want to combine those two operations? Can I do that? Addition and scalar multiplication? Absolutely. So let's do an example of that. So given A is equal to 1, 2, 3, 4, and B is equal to -1, 5, 0, 7, compute 2A minus 3B. And the nice thing about matrices compared to like the first exam material where it was like partial derivatives and all that stuff, it's way simpler because we're not dealing with derivatives and all of that stuff. We're just looking at numbers and making sure that we're following this structure, right? So it's a much slower concept than, say, calculus. So plugging in. But there are elements of this that do kind of go off the deep end and get a little bit more complicated. But luckily for us, we're not going to get too deep into those topics. So I'm just replacing A with the matrix A, and I'm replacing B with the matrix B. And there we go. And then according to what we just learned about scalar multiplication, I am going to distribute, right? So distribution of the 2 into each one. Now, do you have to show this level of work? Absolutely not. You could just do this all on your calculator. But again, it doesn't hurt to see it a couple of times by hand, because that makes you understand it better. Now, one question that gets asked is, do I need to distribute the minus sign into the matrix? You can choose whether or not you want to. So I noticed that if I leave the minus sign outside, then I don't have that many negative numbers. So it's a personal preference. You could distribute the minus sign. However, if you distribute, then you would have plus, and then it'd be -3, ... right? Like it'd be like that. Like you'd have to put a -3 and leave a plus sign outside. So what I've seen people do is they'll distribute the minus sign in there, but then they put a minus sign outside, and you've basically done the opposite of what you wanted to do. So you just got to be careful with that. 2, 4, 6, 8 minus -3, 15, 0, 21. And then we get 2. Now I'm going to make a mistake on purpose, so I want you to pay attention to I making this mistake because many students make this mistake, especially in a 50-minute timed exam environment. They're easy to slip up like this. So notice that I messed up one of the entries. And that entry is the top left corner because I wrote 2 minus 3, but it's really 2 minus -3. So it's actually like that, which would be a +3, right? So many students make that mistake because of just, the stress of the speed of the exam. So 2 plus 3 is 5, -13, 6, and -13. And there we go. So I've combined those two concepts of scalar addition and, scalar multiplication and matrix addition. And I can make you do other things, but that's the basic principle. So we have to introduce a new kind of operation that will be different than pretty much anything you've seen before. And that's going to be the matrix transpose. So this is a very useful operator in matrices because sometimes a matrix has what you want, but it's just not in the correct structure. And what I mean by that is the rows and columns aren't correct. So let's say you're designing a database and you basically take a bunch of numbers in because someone is inputting numbers and you organize your data in columns because you like columns, right? So your data is a bunch of columns like this. All right, that all your numbers are in here. But someone else, when they take in the data, they do rows, right? 1, 2, 3, 4, 5, 6, 7. The data is the same, like these have the same data, but they're just not correctly matched up. So your database doesn't like that. It has a very peculiar structure. You like columns, this person likes rows. So, but the data is the same. So what if I could just make one of them the other one, right? What if I can change this row into a column? Would that be possible? And the answer is yes. So we do this a lot in a language called MATLAB, where we're trying to find like inputs and outputs. And so when we do our inputs, they're like a row of numbers, but then our outputs become a column, right? And we want to plot them like on a graph. But the thing is, MATLAB doesn't like when they're different. They have to be either both rows or both columns. So we use the transpose to make one of them into the other, like a row and a row or a column and a column, so that we can properly plot. It doesn't change the numbers. It just changed how they look. So that's kind of the matrix transpose in a nutshell. It's just to make it look how we want it to. And so how do we do that? Well, like this. The matrix transpose, the transpose of a matrix is better saying that. The transpose of a matrix A, and the way we denote this is using a capital T. So A transpose is the matrix where you swap columns into rows or rows into columns. Now, there's a much more rigorous and formal way of saying this, but it just becomes a bunch of subscripts and stuff like that. So it's not that big of a deal. But essentially, and this is just better learned by example, honestly, if you say let A be equal to, and just to really exaggerate it, like that, let's find the transpose of A, okay? And so what happens is, I'm a column into row person. Sorry, no, a row into column person. But some people like to do row, what's it called? Columns into rows. It's a personal preference. So one thing to notice is that this matrix has 2 rows and 4 columns. So when you do this, and you do the transpose, okay, the new matrix is going to have the reverse, 4 rows and 2 columns, right? So this entire row becomes column number 1. 1, 2, 3, 4, 1, 2, 3, 4. This entire row becomes this entire column, 5, 6, 7, 8, right? And that's a transpose. And let's just color coordinate that a little bit so we can see. And that's how you take the transpose. Now, are you going to do the transpose a lot? Not really. But it's something that's very useful in linear algebra, like really, really useful. So see, note that an m by n matrix becomes n by m. It swaps the dimensions. They become the opposite of each other. So that's cool. Now, if you're wondering, yeah, I don't want to do that because my ability to see numbers isn't great. Well, your calculator can do it for you. So if you do second matrix, you press A, and then you hit the second matrix button again, hit the right arrow key, go to math. Option number 2 has a capital T for transpose. You press enter again, and there you go. It does it for you. So the calculator in this exam, more than any other exam, is the most important tool because you'll use it a lot. Actually, you could argue the next exam, the probability stuff is equally just as important with it too. But that's a transpose. So now we have a way of manipulating matrices by their dimension. So let's do an example of that. So now we're going to combine matrix addition, scalar multiplication, and the transpose. So compute. Let me do it the other way around. Let A be equal to 0, -1, -2, 0, 1, -1, and C be equal to -1, 1, -1, -1, 1, 1. Compute A transpose plus 3C transpose. Now, if you're wondering, is there an order of operations to matrices? Yes, there is, and it's the same as numbers. PEMDAS, parentheses, exponents, multiplication. There's no division, and then addition, subtraction, right? Left to right, you always do left to right. So yeah, there is a PEMDAS. So step 1, do the transpose first. So because it's kind of like the exponent. It's not actually an exponent. To be clear, it's not an exponent, but it's like our exponent, right? So you do the transpose first. So A transpose is going to be equal to, so row 1 becomes column 1, -1, sorry, looking at that incorrectly, 0, -1, -2, 0, and 1, -1. And you just actually have to write it out because just looking at it sometimes is very confusing because of how the numbers look, especially when they're all very similar numbers. So if you're watching this, I really recommend that you actually write it out and not just like look at it, because the only way you train your brain to get better at these is by actually writing them out. And that's the key thing about matrices is they look easy sometimes. Like sometimes they look easy to do, but it's the muscle memory of doing it that's just as important, if not more important, than actually understanding what you're doing. Okay. And so if I take the transpose of C, I get -1, 1, -1, -1, and then 1, 1, right? Like I said, when the numbers look as similar as they do in matrix C, it starts to kind of blur and you can barely tell which one's which, honestly. And then blue. There we go. So now we have our transposes, okay? Now, could you multiply the number first and then take the transpose? Absolutely. That would still work because it doesn't affect the order of operations there, but I would always recommend doing the transpose first. Step 2, plug in. So A transpose plus 3C transpose becomes 0, -1, -2, 0, 1, -1, plus 3 times -1, 1, -1, -1, 1, 1, And then I'm going to do the multiplication. And a lot of people just do this in their head, which is fine. Like there's nothing wrong with that. Just be careful. It's very easy to make mental errors. And say on the exam, if this is like a free response type question, if you use your calculator and you get it wrong, there's nothing to grade, right? So there's no partial credit to be given if you don't do it correctly by hand. But if you do it correctly on your calculator, depending on the instructor, maybe um, they don't require you to show work. It just depends. Now, I should be very cognizant of doing that. So plus, you don't have to write plus -3. You could do 0 -3, just to be consistent because we're adding. But you can use all of your rules of algebra, or real numbers, I should say, where plus minus becomes a minus. I'm just making sure that I'm consistent here. -1 plus 3. And then we get -3, -5, 4, 2, -3, and 2. One funny thing, just teaching this class so much in terms of linear algebra, sometimes -1 plus 3 will be equal to -2 in your brain. Like, again, when you do these too many times, you'll just make silly mistakes like that. And you just got to be careful. Like, that's the thing I say in linear algebra. Patience is king. Um, but sometimes you'll just make silly mistakes that you cannot avoid. Now, if you want to do something like this in your calculator, you can, and this is very important because people will kind of do some of it by hand and then the rest on calculator. You either do it at the very beginning in your calculator or you commit to doing by hand. Don't ever mix it, because if you do, then you might accidentally like do some work and then use the original equation, and now you've kind of messed up the entire problem. So either you do the calculator at the beginning or don't do it at all. So second matrix. Now, one interesting thing is I use the letter A and C here, but my calculator uses A and B first. So I always tell students, if you can match the letters, by all means do, because it makes it easier for your brain not to mess up. But you won't always be able to do so. So you have to be comfortable. Now, one little trick I teach students is if you want to redo your matrix, like you're making a new one, make it a 1 by 1 matrix. So 1 by 1, put the number 0, and then now go back up and then put the dimensions. So the dimensions would be 2 by 3, sorry, 3 by 2, 3 rows, 2 columns. And so now it zeroed it out, because I've had students like use old matrices and they forget to change one number and then their answer is wrong because they thought it was part of their matrix. So let's do 0, enter -1, -2, 0, 1, -1. So there we go. Second quit, second matrix. And because I use the letter C, I'm going to use letter C. Okay, you don't have to do that. It's just my recommendation. And again, look at me using my original matrix, not the transpose ones. That's because I wanted to do it by hand. But if you're going to use your calculator, use the original ones. Don't use the new ones. Okay. So I got that. Second quit, second matrix. So we need A transpose. So A. Second matrix, math. Option 2, you can just press the number 2 and that'll do the transpose. Second matrix, C. So you can hit the number 3 to do C, but I need a plus sign. So second insert, plus. Second insert allows you to put something in case you ever miss it. And I forgot a 3. So second insert, 3. And then second matrix, again, if you want to use math for transpose, and then option 2, so you can scroll down or hit 2. And then press enter. And let's check our answer. -3, -5, 4, 2, -3, 2. So yeah, we got the same answer. So that's how we can combine all of the operations into one problem. All right, so let's just do one more example of something you might see in 5.1. And that is, okay, now let's kind of introduce the notion of two matrices being equal to each other. So the equality of matrices. So don't overthink this, because there is a way of kind of, sending yourself into a deep spiral if you overthink this. No one really argues that 5 equals 5. Like, we're all in accordance that those two are the same thing. And so how do we say that about matrices? Well, matrices are basically the same concept. Two matrices are equal. This is for numbers. So two matrices are equal if they are the same dimension and have the same values in each entry. So the simplest example, 1, 2, 3, 4. 1, 2, 3, 4. Like those two matrices are equal to each other because they look exactly the same. And that's the best way of thinking about it. Two matrices are equal if they look exactly the same. Now, why do I bring that up? Well, technically speaking, what if, and you don't need to write this down, but just think about it. What if I had a matrix that looks like this? Are these matrices equal to each other? Well, one could argue, well, they have numbers and they have the same four numbers. Yeah, they're in different spots, but who cares, right? They're the same numbers. Well, matrices care about where the numbers are located. Their location is important. So these are not equal to each other because even though they have the same four numbers, they're not in the same spots. And there are other areas of mathematics where we don't care about order. And so they might be the same thing. And we'll talk more about that in chapter 7 with set theory. But again, don't write this down because it's going to come later. If I have the set 1, 2, 3, that is equal to 3, 2, 1 as a set because set doesn't care about order. It just cares about what's in there, right? If me, John, and Joe are going to, the store, it doesn't matter where we sit in a car because it's the same three people, right? We don't change depending on where we sit. We are the same three people. So that's why we care about this notion of equality in matrices, and we have to be very specific. It's where they look exactly the same. So I bring this up because there's going to be a question on the homework potentially where you basically have to find a matrix that is equal to another matrix using variables. So this is how they're going to word it for you. Solve for xy, zw if x plus y, y plus z, z plus w, and w is equal to the matrix 3, 5, 7, 4, right? And so I want you to think about this. Well, you just said right now that two matrices are equal to each other if they look exactly the same. So what matrix is equal to 3, 5, 7, 4? Well, it's the matrix 3, 5, 7, 4. Like that's the only matrix that's equal to it, which means what number has to be equal to what? Well, the top left corner has to be equal to the top left number. The top right number has to be equal to the top right corner. The bottom left corner has to be equal to the bottom left corner, and the bottom right corner has to be equal to the bottom right corner. And that's fundamentally how you solve these. You just set the corners equal to each other and solve. So let's do that. Each corner is equal to the other corner. So x plus y is equal to 3. Y plus z is equal to 5. 2 plus w is equal to 7. And then w is equal to 4. And we notice, okay, w is equal to 4. So we got the first one. Thus, I'll do it over here. We can plug this 4 into this w right here. So z plus w is equal to 7. So z plus 4 is equal to 7. So subtract the 4 over, z is equal to 3. Right? Now we got our next number. So then I can plug in this z equals 3 into here. So then, and y plus z is equal to 5. Y plus 3 is equal to 5. Y is equal to 2. And we got the next number. And then lastly, all these arrows are going everywhere now, but that's okay, right there. X plus y is equal to 3. X plus 2 is equal to 3. X is equal to 1. Subtract the 2 over, you get 1. And there is our answer. Now, we'll learn this later, but you write this answer in the most efficient way as X, Y, Z, W equal to, and then just make sure, I think the homework will probably make you write it like this, so just follow the order that they tell you. 1, 2, 3, 4. Is it a coincidence it's 1, 2, 3, 4? Absolutely. Yeah, that's how you solve these matrix algebra type problem. You just set the top left corner equal to the top left corner and just kind of solve. And that's pretty much it.